Hi everyone. In this video I'm going to show you how to set up a monohybrid cross, which is typically what you would call a simple punnett square. Now for a monohybrid cross, we use this particular type of punnett square when we only have one trait. Okay, so the word mono means one. Okay, so we're looking for one trait that is affected by two alleles. Which are basically two different types of genes. Okay. Now, in most cases, these are dominant recessive alleles. So dominant and or recessive. So I'll give an example. We'll use hair color, because most of us already know that for human hair color, brown hair tends to be dominant. Okay, so we're going to use big B to represent that particular allele. Okay. Blonde hair is recessive. So we'll use lowercase b to represent that particular allele. So let's say you have a scenario where the mother, okay, now for females, we'll use the symbol that looks like this to represent females. Let's say the female has brown hair, and let's say the male, dad, and sometimes we'll use this symbol to represent males. Let's say dad has blonde hair. So what would the genotypes be for mom and dad? Because what we have right now, this is just the phenotype. It's the physical characteristic that you see. But for genotype, okay, the easiest one to figure out is dad. Because dad has blonde hair and blonde hair is recessive, the only way to get this particular genotype is for dad to have two recessive genes. So dad's genotype is small b. Mom's genotype, we know, has to have one big B, at least. Now, it's the other one that's in question, right? Because we don't know necessarily what it is. Okay, so there's two possibilities. Mom could be big B, which is homozygous. Or mom could be big B, heterozygous. Oops. Okay. So let's just for now, assume that mom was homozygous. Okay. If mom were homozygous, and we want to find out what their children would be like, then we basically are setting up a punnett square or a monohybrid cross with these two parents in this particular fashion. Okay. So you set up a grid. It's a 4x4 square. Okay. It really doesn't matter which genotype goes on the top or which one goes on the side. Okay. Usually the males are the ones that they put on the top and the females are on the side, but it really doesn't matter. Okay. So even if I put mom's genotype at the top, I would have it so that each allele is occupying its own little square, okay, just right above that square. And the same thing with dad. Okay. So this is mom's genotype. This is dad's genotype. These guys here, these boxes, they represent the offspring's genotype, or the offspring's potential genotype. So in this cross, we just pair up the alleles. Okay, and this is basically Mendel's law of segregation and pairing. So they split up easily, right? And once they split, okay, mom provides one big B, dad provides a small b. They pair up in different combinations. So in this case here, you'll notice that when we take big B and small b, big B and small b, big B and small b, all the offspring have the same genotype. Okay. All of them are 100% big B, small b, which means their phenotype is brown. So 100% brown. Because every one of them has at least one dominant gene, and that dominant gene overpowers the recessive. So that's where your law of dominance fits in. And to make this Punnett square works, this is where your law of segregation and pairing comes in. Okay? So that's one possibility. These offsprings is known as the F1 generation. Okay. The parents is the P generation. Okay. Parental generation or parent generation, P for short. The other possibility, though, is what if mom was not homozygous dominant, but heterozygous dominant? What would all the offsprings look like now? So in this situation, let's set it up so that mom is heterozygous, dad remains homozygous, recessive, or just recessive, because you can only be recessive by being homozygous recessive. Okay, so this time around, when we do the Punnett square and fill it in, we notice that over here, mom is contributing a small b, but so is dad. Okay, mom contributes a big B, dad contributes a small b, both contribute a small b over here. Now, your F1 generation have different genotypes now. 50% of your F1 generation is big B, small b. The other 50% is small b, small b. Okay. This is called the genotypic. Oops. Let me just slide this back over. This is called the genotypic ratio, because we're telling people what the genetic makeup is. Okay, what percentage is what. Okay. When we take a look at what they look like, well, this half here have brown hair. So 50% is brown hair. And this half here is the one that's different, right? This is 50% blonde hair. This is called the phenotypic ratio. Move over a bit. Okay. So in these two scenarios, the parents both seem identical. They both seem to have mom with brown hair, dad with blonde hair. But because of the difference in the mom's genotype, it makes a significant difference in what the offsprings could be. So in the first situation, the genotype or genotypic ratio and phenotypic ratio, they're both 100% brown. Okay, and they're both 100% big B, small b. But because the mom in this second scenario is heterozygous, we now see that the children could potentially be blonde. So this is a very typical example of a monohybrid cross. And we can use monohybrid crosses to help us to predict how these genes would pass on to the offspring and what the potential outcome might be. So the next time I see you in class, we'll look at a few more of these scenarios. Thank you.